be talking about today is how we classify the concentration of a solution and how do we calculate it. The concentration of a solution is the measured amount of solute. So like we said, with our salt solutions, if we have two salt solutions with the same amount of water, but different amounts of salt in them, then those solutions have different concentrations of salt. So there's your word for the day, concentration. If you only put a little bit of salt in a solution, and then like I said, a beaker of water, say 400 milliliter beaker of water, you only put a little bit of salt in it, it is a dilute solution. If you put a lot of salt, like if you saturate that solution with salt, it is a concentrated solution. So those are the words you're going to, the kind of vocabulary we need to remember today. Concentration, dilute, and concentrated. This is the word, this is the concept that chemists use for discussing concentration of solutions. Molarity. Big M, okay? We write it as a big M. Molarity is the number of moles of a solute dissolved in 1 liter of solution, okay? So what we have is moles of solute over liters of solution. Now in my example of a salt and water solution, what is the solute? Put salt in to water. What's the solute? Salt is the solute. And what is the solution? No. No. Salt is the solute. The solution is salt and water together, okay? When you add the salt to water, the volume might increase slightly, okay? So it's not just the volume of the water, it's the volume of the water and the salt. So let me write that again. Moles of your solute over liters of your solvent plus your solute. Does that make sense? You just measure whatever you end up with, whatever the volume you end up with. How many moles of solute do you put in it? Okay? And we also call that molar concentration. So you might be asked, what's the molar concentration or what's the molarity? Molarity, moles over liters. And I think there's probably a simple mnemonic. Mole, liters, molaritors. I don't know, but you guys can remember that. I'll give you a sheet later, cheat sheet. And here we go. This is how you make, this is the laboratory technique that you use to make a solution, okay? We use what is called a volumetric flask. Do you see that? Now, a volumetric flask is kind of interesting. It has a big section right down here to fill, and then when you get very close to 1 liter, there's a mark right up here on the neck of this flask, okay? And it's really skinny there, so even just adding a couple of drops makes the level rise really close, a whole lot up in this neck, so you can really see that you're exactly at 1 liter. So if this were a 1 liter, and it is, this is a 1 liter volumetric flask, the mark up here is 1 liter, okay? When you filled it up to that mark, you have exactly 1 liter. And the way you make a solution in a volumetric flask is you fill about halfway. So they used half filled with distilled water, and they're putting in their solute. Now they're trying to make a 0.5 molar solution. Now remember, if it's a 0.5 molar solution, it has 0.5 moles of solute, whatever you're dissolving, and 1 liter of solution, not of water, okay? Because if it was 1 mole per 1 liter of water, you would go ahead and fill this all the way up to 1 liter, and then put in your solute. But you might actually see a little bit of a rise, so it might be more than 1 liter. What you do, you fill it halfway, you put in your 0.5 moles of solute, right there, and then you swish it around until what happens? Mixes or it dissolves into solution. Now, in this step, you have all of your solute dissolved in your solvent. And what's the last step to get exactly 1 liter of solution? You fill the rest of the way up to the 1 liter line. Now you have 1 liter of solution that has water and 0.5 moles of solute, okay? Another way to say that is it has 0.5 moles of solute in enough water to create 1 liter, okay? Does that make sense? And so what you know is you have 0.5 moles of solute over 1 liter of solution, and that is a 0.5 molar solution, okay? Pretty simple concept. Moles over liters, okay? I'll move on. There is your equation. I will put that on a piece of paper for you. Molarity, the big M, is moles of solute over liters of solution. How do you calculate it? This is sample problem 16.2. Go ahead and get your books out. Okay, so we're going to calculate the molarity of an intravenous saline solution. Okay? They're often administered to patients in hospitals. You've seen it in your medical shows where the bag is hanging on the stand and there's a tube that runs to a needle that's in their arm. Okay? The saline solution that we're talking about contains 0.9 grams of sodium chloride and exactly 100 milliliters of solution. Okay? Everybody good with that? Our first step here, did they give us moles of solute or did they give us grams of solute? They give us grams. How do we convert grams? We're going to have a conversion factor. How do we convert that to moles of sodium chloride? Anybody remember? We need to get out our road maps. Yeah, molar mass. Moles of NaCl over grams of NaCl. Over grams. So they gave us 0.90 grams of sodium chloride. What is the molar mass of sodium chloride? You will need calculators. Is it something like 58-ish, 58.5 or something? So 1 mole, everybody remember this? If you need to get your road maps out, you can. 58.5 grams. So how many moles do we have? Can someone do the calculation for me? Our grams of sodium chloride cancel, and we're dividing 0.9 by 58.5. Two significant figures, nice. So round to 1.5, or is it 1.5? What's the next digit?
3.
Perfect, we got it. Okay, so that's how many moles we have. Now we just need to put that over what? To get molarity, it's moles over mole over, yeah, but exactly what volume? Moles over liters, okay? Did they give us liters? They gave us milliliters, so what do we have to do? Good morning. What do we have to do? They gave us 100 milliliters. Anyone help me out? Convert it to liters? Perfect. How do we do that? Using a conversion factor. What's the converting factor? We need liters where? On top? Really? How do we get the milliliters to cancel if liters is on bottom? What do we need on bottom? Milliliters. Can you tell me how many milliliters there are in 1 liter? 1,000. So, how many liters do we have? Did you guys do that? A tenth of a liter? Is that right? Do we have what we need to calculate molarity now? We have moles and we have liters of solution. Shall we? Molarity equals moles of solute over liters of solution. And I'm going to write solution like that just to save a little time here. 0.015 moles of salt NaCl over 0.1 liters of solution. And the molarity is, so 0.15 is the molarity. So what they got in the book? Awesome. Now, together we're going to work number 10 and 11 in the book. Okay, so for the guided problems that we're going to turn in at the end of class, for 10 you should have gotten 0.1 molar, and for 11, 2.8 molar. And moving forward. So let's do sample problem 16.3 together. Now we're going to turn this around and we're going to use the molarity to determine how many moles we have in a particular volume of solution. So it's the same calculation, it's just slightly changed. They have given us bleach. It's a dilute aqueous solution. That means it's a solution where the solvent is what? Water. When we have an aqueous solution, that means that the solvent is water. And that means that sodium hypochlorite is the water, the solvent. Sodium hypochlorite is what we put in the solution, and we call that the solute. Exactly. This is the solute. How many moles of solute, that's what we're solving for, are present in 1.5 liters of a 0.7 molar solution of NaCl. So, they gave us big M equals 0.70 molar. And they gave us a volume of 1.5 liters. And if our equation is that molarity equals moles over volume, all right, moles over liter, should I write that? I'm just going to leave it like this. How do we solve for moles, the N? What do we have to do to this equation? Multiply both sides by, so we get M equals molarity times volume. And in this instance, we've got 0.70 moles. Molarity. The units are moles per liter for molarity. And volume is 1.5 liters. The units of liters cancel, right? And all we're doing is multiplying 0.7 times 1.5. I bet it's going to be something like 1.05. Is that right? Liters. And do I have it in the right number of significant figures? How many significant figures here? 2. How many here? 2. So this is really 1.1 liters. Oh, not liters. I got more liters. Wait. Liters canceled. This is moles. Moles of sodium, what do we say? Hypochlorite. And now you can do 12. Everybody good with that? You can do number 12 and 13 on page 527. And for number 12, we get 0.142 moles of ammonium nitrate. Everybody get something like that? As a review of 13, they gave us volume in milliliters. We convert it to liters. They gave us molarity. We do our calculation where we multiply molarity times volume to get moles, but we're not done because they asked for grams of calcium chloride. So we use the molar mass right here, just 111. And we get to two significant figures, 56 grams of calcium chloride for number 12. Let's move on. What we have next is, it's a pretty simple one. Just a check problem. How much water is required to make a 1 molar aqueous solution if we're using sodium chloride? And we have 58.4 grams of sodium chloride dissolved. Where do we start? We know mass, we don't know moles. What is molarity? Does anyone have any idea where to start with this? So 58.4 grams of NaCl is 1 mole. So we know the volume of our solution, if we want a 1 molar solution, needs to be 1 mole over 1 liter of solution. Remember, this is solute. We have this, so we need enough water to make what? Enough water to make 1 liter of solution. Everybody good with that? And here's what happens next. Sometimes we start off, in fact, when we do labs, which we'll be doing after the SOL. See ya. Have a good day. So you know what's due tomorrow, right? When we start doing the lab, a lot of times I have very concentrated acid in the lab cabinet, like 5 molar, okay? We never have to use anything that concentrated. We might use something more like 1 molar. So let me ask you this. What do I have to do to acid that's 5 molar acid? What do I need to do to get it to be 1 molar acid? Just generally, what would I do? Take out a bunch of the acid, run my hands right off. What's a very simple way to create add more water? It's called diluting, exactly. We dilute, okay? So check this out. If my solute is blue, can you see how this is a really dark blue? And if I add a bunch of water, it's a light blue. Have I added any solute between these two? I just added water, okay? Do you see this magnified version here? My solute particles, there's a whole lot of them in 1 drop, right? There's a lot of them. If I add water, what happens? There's fewer solute particles per water molecule, right? So these are the same solutions. You remember my first question when I kept saying, if we have two salt solutions that are the same volume, the same temperature, what could be different about them? What could be different about them is the amount of solute per liter, okay? The concentration of the solute. So what we're going to be talking about next is, now here you can tell by the color that that this one's more concentrated right here than the other one. Solution A right here would have a higher molarity. It has more moles of solute per liter, okay? I add water, like I'm diluting acid in the stockroom, and I end up with a lower molarity solution. I add more solvent, I make it lower molarity. Here's the thing. Did the moles of the solute before I diluted change? Did I add solute? All I added was solvent, okay? So the moles of solute before dilution and the moles of solute after dilution are the same. Knowing that, you can rearrange to solve for moles of solute, just like we've been doing, molarity and times liters of solute solution. And the moles of solute are the same. So guess what we can do? If we get the first molarity 1, before we diluted, and the volume before we diluted, it will always equal molarity 2, and volume 2. Right? Because my number of moles, my moles of solute, they don't change. I don't put more solute in. I only change the solution, so the volume and the moles change. The molarity and the volumes change, but the number of moles don't. They're the constant. So, I end up with that equation right there. Total number of moles of solute remains unchanged upon dilution. Okay? These are from the initial M1 and V1, or the initial solution, and the M2, V2 are diluted. This is what it looks like in the lab. The student is preparing 100 milliliters of a 0.4 molar magnesium sulfate solution from stock solution. This is what she'd get out of the stock. That would be very concentrated, 2 molar solution. She only wants a 0.4 molar solution. And she wants 100 milliliters of it. Okay? So she measures in 20 milliliters of the stock solution. She transfers that to 100 milliliters, volumetric flask, and then adds water until she's up to 100 milliliters of solution. What does that mean? Let me ask you this. How many moles does she have right here per liter? 2 moles per liter, okay? 2 moles per liter. And she knows she only needs 0.04 moles, right? She's going to try to make this solution, 0.4 moles per liter. So here's how it works mathematically. Basically, she's adding a small amount of very concentrated solution and diluting it with water. And here we'll do ours. How many milliliters of aqueous 2 molar magnesium sulfate must be diluted with water to prepare 100 milliliters of aqueous 0.4 molar magnesium sulfate? What's this one right here? Molar 1, molar 2, volume 1, volume 2. Which one is that? Molarity 1. They gave us that. What is this one right here? Volume 1 or volume 2? She's trying to prepare a 100 milliliter solution. That's volume 2. Because they're asking how many milliliters must you start with, okay? And this is your moles too. So they're asking us to solve for volume 1. Okay? Let's do that. Molarity 1, volume 1 equals molarity 2, volume 2. They gave us molarity. Let's switch these around. We're going to divide both sides by molarity 1. And then we're going to plug and check. It's just a plug and check type problem. We want 0.4 molar solution, and the volume of it, we want 100 milliliters. In this instance, do I need to change milliliters? Or can I keep them because my answer is going to be in milliliters, right? And I'm dividing by the initial molarity, which is 2.0 molar. Molar cancels, and I'm left with milliliters. So I'm going to start with 20. This is going to be 4 divided by 2 milliliters. Is that right? I'm going to have to get the calculator. 20. So we start with 20 milliliters. Now you can work numbers, I think 14 and 15 on page 529. I'll help you set them up. In problem 14, we don't know the initial volume, but we do know volume 2, molarity 1 and 2. Molarity 1 is 4 moles. And then 4 molarity. Molarity 2, when you want to dilute, you want to get a 0.760 molar solution. And the final volume that you want is 250 milliliters. Since we can give our answer in milliliters, do we need to convert milliliters at this point? No. If you do convert, is it an error? No. Won't hurt you. When you're calculating molarity, you must convert to liters. If you're calculating volume, you can leave it as it is. Our equation is M1 V1 equals molarity 2, volume 2. We're looking for our unknown is volume 1. So we're going to solve for volume 1 first by dividing by both sides by molarity 1. Then we're going to substitute. Our initial molarity is 4.0 molar, and we're trying to get to 0.760 moles. And the volume is 250 milliliters. And it is a plug and chug. Percent by volume. It's the ratio of the volume of a solute to the volume of a solution. It's very useful when you're mixing liquids, okay? Because we normally don't measure the volume of a solid. We don't normally use this when we're, say, putting sugar in iced tea or salt in water. We normally measure the mass of the solid. This is normally used for liquid type solutions. So ethanol in water is a good one, okay? Here is the same old percent equation. Part over whole. Volume of solute is your part. Volume of your solution is the whole. Okay? And solution means once you've combined both of them, okay? Volume of solvent is not what you're concerned about. Volume of solute over volume of solution. That gives you a percent by volume. And we use it again. When do we use it? When we have two liquids. Okay? It's easy to measure the volume of a liquid. It's not so easy to measure the volume of a solid. Okay? What is the percent volume of ethanol in the final solution when 85 milliliters of ethanol is diluted to a volume of 250 milliliters with water? And that's pretty simple. Percent by volume equals part, which is 85 milliliters, over whole, 250 milliliters, times 100 equals, and I'm going to need my calculator for that, but it's about 21, I think. 85 divided by 250, 134, there we go. That's a third, my bad. Times 100 equals 34%. So this solution will be 34% ethanol. Everybody got that? It's pretty simple. It's just percentage. It's the solute, which is ethanol, 85 milliliters, and it's the diluted solution. Here's the one thing you need to be concerned about these. If they give you two different units, like milliliters of solute over liters of solution, you need to make sure that the units cancel. You see that? And that was the practice problem, I believe. So you can now do numbers 16 and 17 on page, drum roll, 530. Okay, just as a complete wrap-up, not only can we use volume percent, but we can also calculate mass percent. And again, it's part of our whole, nothing really exciting. Got it. And lastly, today we learned three ways to calculate the concentration of a solution. We used molarity, percent by volume, or percent by mass. Okay, the main one I want you to remember is molarity. That's how chemists typically describe concentration. And let's do it real quick, percent by mass, and then we will be done with, here we go, how many grams of glucose are needed to make 200 grams of a 2.8 glucose solution? So we know we have 2.8 is our percent by mass. We have a part, which we don't know, that's 6 grams. And we have a whole, which is 2,000 grams, times 100. So to do this calculation very quickly, to find X grams of glucose, we need to multiply 2.8 by the 2,000 grams and divide that by 100. And when we do that math, we're going to get 56 grams of glucose. Now you can do number 18 in your book, and here it is right here. These are the 4 equations that you're going to have to know to calculate concentration of solutions. And again, back to this, we learned 3 ways to calculate concentration. Molarity, that's the big M, percent by volume, and percent by mass. We can use this for anything. This is very valuable for calculating liquids, and this one maybe for solids.